Good morning, students. Today we are going to start our new chapter. That is the fourth chapter. That is active filters using operational amplifier. So, in this active filters, what are the concepts we are going to discuss? Generally, filter is a circuit where it is required for the suppression of signals according to their frequencies. So, according to the frequencies, the filter is going to separate the signals. These are mainly used in communication systems. In communication systems, we are going to use these filters where signal processing has to be done, and in several electronic equipments, so we are using these filters. These filters can be implemented by using passive components as well as active components. So when we are using passive components, generally, we are going to use the resistors, capacitors, and inductors for filters, for obtaining the filters. Whereas in this chapter, we are going to discuss about active filters. So active filters is nothing but it is an electric circuit, that is frequency selective electric circuit, that passes the electrical signals of specified band of frequencies. So it only passes the selected electrical signals of specific band of frequencies. You have to keep this in your mind, and attenuates other frequencies. So it only selects a band of frequencies and attenuates other frequencies. Okay. Filters may be of two types: analog filters as well as digital filters. Whereas here in this chapter, we are going to discuss about only the analog filters. So, analog filters. So, in this, we are having, we are going to discuss about what are the different types of filters and what are the advantages of active filters, and inactive filters, types of active filters we are going to discuss about, and the characteristics of that filter. Next, according to the types, there are different types. That is, we're going to discuss about active low pass filter, active high pass filter, active band pass filter, and active band stop filter. Then finally, we're going to discuss about, so we're going to see about all pass filter also. So these all are the filters we are going to cover in our chapter. And coming to the introduction, so a filter, which is a circuit that passes only the signals with a specified band of frequencies and rejecting all other frequencies, nothing but. So a specified band of frequencies, it allows only a specified band of frequencies and rejects all other frequencies. So that is called a filter. So because of this property, the filter is also called as frequency selector. Because of this property, we can call this filter as a frequency selector. Here, as it is selecting the frequency, that is, as it is selecting the signal which is having a particular frequency. So it is also called as frequency selector. Frequency selector. And coming to passive filters. So passive filters are built with passive components. That is, we are having the passive components like resistors, capacitors, and inductors. So if the filter is designed using the passive components, that is capacitors, inductors, or resistors, then it is said to be a passive filter. So these three elements are passive elements. Why these are called passive elements means they just passes the signal. They just passes the signal through them. They will attenuate, but they are not going to increase the strength of the signal. So because of this reason, these components are called as passive elements. So in case of active filters, so we are going to use an active devices. Either they may be a transistors. So active devices means they are not only passing the signals, but they are also boosting the signals. That means they are also increasing the strength of the signals passing through them. So because of this reason, these filters are called active filters. So here in our chapter, we are going to use operational amplifiers as active element. As active element. So we are going to discuss about that operational amplifier filter in this chapter. Also, opamp can operate in two modes. So non-inverting mode as well as inverting mode. So opamp has an advantage that they provide gain, high gain, and attenuation will be less. So opamp here used is in non-inverting configuration. When coming to this non-inverting configuration, it offers a high input impedance and low output impedance. This will improve, which will improve the load drive capacity. That means it can be able to drive the load and is isolated from other networks, other circuits. So now these filters are used in communication and signal processing circuits. They are also employed in wide range of applications such as entertainment and medical electronics also. So this is the introduction, and coming to advantages of active filters over passive filters. We can design active filters which provides, as we have discussed now, that op amp is an active element which provides high gain. So here required gain it is going to provide, and attenuation will be also less in case of active filters. And there will be also no loading problem because it can drive large loads. Active filters can drive large loads because they are having high input resistance and as well as low output resistance. And these active filters are cost effective, and these are available in markets also. Easily we can access them, easily we can buy them in the markets. They are commercially available, commercially available. And coming to now, we are going to discuss about what are the different types of filters. So there are basically there are four types of filters, that is low pass filter, high pass filter, band pass filter, and band reject filter. Based upon the frequency response, we are going to divide these filters as low pass, band pass, band reject, and high pass filters. So if we are going to discuss about one by one. So coming to here, you can see. So this is the a response of a filter, response of a filter circuit. This is the response of a filter circuit. Here in this filter circuit, so here in this filter circuit, so here in this filter circuit, you can see, if you observe the frequency response of this filter, on x-axis we are going to consider a frequency f, on y-axis we are going to consider the gain on y-axis. So in decibels, we are going to take the gain in decibels. So see here, this the blue line which shows the response of the filter. So at some frequency, up to some frequencies, from zero frequency to from lower frequency to up to FC, you can observe that the response of the filter is resembles like a flat response. After that, you can see the filter response is going to attenuate. That is, the filter response is going to decrease towards a zero dB. At high frequencies, it is going to zero. It is going to zero. So in this response, you can see wherever the flat response is there, so that region we are calling as pass band, and we are telling that pass band as the bandwidth of the filter. Pass band as the bandwidth of the filter. So where this pass band, how we are going to select this pass band? So through a critical frequency FC. So this FC is specified by the components which we are using in the filter. That is like it may be RC components or RL components. So here, as we are discussing about op-amp filters, so as the inductor is heavy, and it occupies more space, we are not concentrating mainly on inductor, and we are going to discuss about only the resistor and capacitor filters. We are going to concentrate on resistor and capacitor filters. So the elements which we are using in this active filters are mainly the resistor and a capacitor. So the resistor and capacitor is going to set a frequency. It is going to select that frequency FC, that is critical frequency. So the frequency, that is the frequencies below this FC is going to be treated as a pass band uh, in this filter case, and above FC is said to be a stop band. That means the attenuation is going to be done in stop band because it does not allow the signals in this stop band. Okay. Hmm. So this is also called as the transition region. So this is, for example, the filter response will be like this. We have discussed with this, and now we are going to discuss about the low pass filter. Now we are going to discuss about the low pass filter. So here you can see what is a low pass filter. So the name itself indicates that low pass means it allows only the signals having low frequencies. It allows only the signals having low frequencies. That is, it allows only the frequencies below the critical frequency level. So it allows only the frequencies below the critical frequency level. So here you can observe that the critical frequency as fh. Here you can see this is as fh. So here we are going to observe the two characteristics. That is, if the filter is ideal, if the filter is ideal, how it is going to produce the response, and if the filter is practical, that is the practical filter, then how it is going to produce the response. Here you can see the filter. Here you can see the ideal response of the filter. So as we have discussed in the last slide, that the filter is having a critical frequency. Here the critical frequency of the filter is fh, and when we are considering the filter as an ideal, so it has the pass band. This is the pass band. Okay, this is the pass band, and this pass band, it will provide a constant gain. A constant gain, that is 1. The gain is equal to 1. The gain is equal to 1 means, how we can say the gain is equal to 1? When the output is exactly equal to the input signal, then the gain becomes 1. So this is how the gain will be obtained for an ideal filter. And in pass band, whereas in stop band, here you can see a straight line. That means there is no any slope. So that means in stop band, it does not allows a single signal to pass through it. It does not allows a single frequency signal to pass through it. So this is the ideal response of the low pass filter. So it is only going to allow the low frequency signals, whereas that is the pass band is during the low frequency signals, and whereas at high frequencies it is going to attenuate the signals. It is going to attenuate the signals. And you can see it here allows the frequencies from 0 hertz to the critical frequency fh, and this critical frequency is also known as the cutoff frequency, which will be set by the RC components in that filter. So this is the ideal response. When coming to the practical response, this will be the practical or actual response of the filter. So here you can see this is a flat portion. The pass band, during the pass band it will be a flat, and during stop band it is not a vertical. In case of vertical, it is going to decay linearly towards 0. That is, the attenuation is also fixed. That is, here you can see minus 20 dB per decade. The attenuation is minus 20 dB per decade. That means as we are going to increase the frequency from fc to 10fc, it is going to decrease minus 20 dB. Then 10fc to 100fc, again it is going to decrease minus 20 dB. Like that, for every decade it is going, the attenuation will be minus 20 dB, minus 20 dB. So like that, here you can see from 0 dB to it falls to for 1 decade, you can see it falls to 0 to 20, minus 20 dB, and after 10 to 100 fc it falls to 20 to 40 dB, and 100 to 1000 fc it falls to minus 40 dB to minus 60 dB. That means the attenuation will be minus 20 dB per every decade frequency. So this is what we have observed. And here the dotted line shows the ideal response of the filter. So this must be the ideal response, but the practically the curve will be line, the blue line here. You can observe that. So this is the practical response, whereas it is we are going to consider the 3 dB below the higher value, 3 dB below the higher value. So from 0 dB is the highest gain, so we are going to take minus 3 dB from this 0 dB, that is nothing but minus 3 dB. So at minus 3 dB we are going to draw a line. So when where that line coincides the curve, then from that point mm, we are going to draw a vertical line. So where this vertical line touches the frequency scale, so then that frequency is called as a critical frequency. That frequency is called the critical frequency. So this is the response of a low pass filter. And we are going to discuss about here the first order low pass filter. So only if we consider only a single RC network, then it is said to be a first order low pass filter. So which consists of only single RC network. And here we are going to see the transfer function of this RC circuit. So here the transfer function H of S, which is given by output by input. Output by input. So output voltage V naught by Vi of S. H of S is equal to V naught by Vi of S. So output voltage, here we are going to take output voltage across the capacitor. So output voltage is given by 1 by CR. And input voltage we are giving to resistor along with the capacitor. So S plus 1 by CR. So if you write the nodal voltage equation at this node, if you write the nodal voltage equation at this node, so we are going to get V naught. At this node, we are going to consider the output voltage. So V naught is equal to input voltage into the reactance of this capacitor divided by the total resistance in this part. So with that, we are going to write this equation, and the equation obtained is 1 by CR by S plus 1 by CR. So we can write as we are going to assume that omega naught is equal to 1 by CR. So in the place of 1 by CR, we are going to write omega naught. So omega naught divided by S plus omega naught. So the H of S will become omega naught divided by S plus omega naught. So now the transfer function, as we know that S is equal to, in Laplace domain, S is equal to j omega. So in the place of S, we are going to place a j omega. H of then this H of j omega is equal to omega naught divided by, in the place of S, we are going to replace it with j omega. So j omega plus omega naught. So that is equal to 1 by, so we are bringing this omega naught to uh, into the denominator section. So when this when this we are going to bring this to denominator section, this will become j omega by j omega plus omega naught divided by omega naught. So we can separate these two terms, that is j omega by omega naught plus omega naught by omega naught. So then it will become like 1 plus j into omega by omega naught, 1 divided by 1 plus j into omega by omega naught. So now by solving that, hmm, so this is the This is the equation, the transfer function of this low pass RC circuit. So here low pass RC circuit means here we are going to give the input to the resistor and we are going to consider output across the capacitor. Across the capacitor. You have to keep this in mind. And h of omega, if we consider the magnitude of this transfer function, then the value will be 1 by root of 1 plus omega by omega naught whole square. So if you want to express it in decibels, 20 log, that means if you want to express the transfer function in decibels, h of j omega in dB, which is equal to 20 log of this value, of this value. And if omega naught is equal to 0, what happens? Omega naught is equal, sorry, omega is equal to 0. So what is omega here? Omega is the input signal frequency. Omega here is nothing but the input signal frequency, as omega naught is nothing but 1 by CR, as we have observed from this. So omega naught is equal to 1 by CR, we know that. And here omega is nothing but the input signal frequency. If input signal frequency is 0, then what happens to this transfer function? So when input signal is equal to 0, the transfer function h of j omega is equal to 1 by 1 plus, in the place of omega we are going to place a 0 divided by omega naught whole square. So 0 by omega naught, so that will be 0, and root of 1 is nothing but 1. 1 divided by 1 becomes 1. So when omega is equal to 0, that is the input frequency of the signal, whatever the signal we have given, the signal, when the signal frequency is 0, then the transfer function of this low pass filter is equal to 1. And so h of j omega in dB, if you write the 20 log, that is equal to 20 log 1. So whereas log 1 is equal to 0, so that is 0 dB. So in decibels it is 0 decibels. The value n, the input frequency is 0. The transfer function of this filter, that is a low pass filter, is 0, is at 0 dB. And when input signal frequency is equal to omega c, which is equal to omega naught, that is equal to, that means input signal frequency is equal to the cutoff frequency or omega naught, so which is equal to 1 by CR. So then what happens? So that means nothing but here omega is equal to omega naught. That means omega is equal to omega naught. So both are equal. So then the transfer function h of j omega is equal to 1 by root of 1 plus omega c by omega naught. So where here we are assuming that here now the frequency of the input signal, which is equal to omega naught. So omega c and omega naught is equal. So this will become 1. So 1 plus 1 square is nothing but 2, root of 2. So root of 2, 1 by root 2. So 1 by root 2 value is 0.707. So this is nothing but the 3 dB frequency. So why we are considering the 3 dB frequency means this with this uh, uh, with this formula you can see that. So and when we are considering the transfer function in decibels, so then the 20 log 0.707, which is nothing but minus 3 dB. So that is why we are going to consider the minus 3 dB frequency for the low pass filter, for the low pass filter. So here omega c, the cutoff frequency, we are going to consider the cutoff frequency omega c, omega c 1 by CR is known as 3 dB cutoff frequency. So when we are considering this the response, here you can see what we have obtained the response. So beyond that frequency, so the output will be, the output is going to attenuate, the output is going to attenuate. So here you can see, so below fc it's zero frequency, and when frequency is 0 or less, the we have observed that the gain will be 0 dB. And at FC, the cutoff frequency, that is omega c or FC. So we can see that it is 3 dB below the upper frequency, that is maximum gain, 3 dB below the maximum gain. So that is 0 minus 3 dB, that is at minus 3 dB we are going to consider. So we are going to draw a line. So it cuts at the this point, and this point is termed as FC. So this is called the pass band. This is how the pass band is designed. So that means here the low pass filter is going to allow the frequencies, is going to allow the signals which is having frequency below FC, which is having the frequencies below FC, and it does not, it attenuates the frequencies above FC. You can see from this graph. You can observe from this graph. And this is what we have discussed about the first order low pass filter. And next, if we consider a low pass filter, that is second order low pass filter. Second order low pass filter is nothing but here we are going to use two RC circuits, which are connected in series. Two RC circuits are connected in series. So when we are going to connect the two RC circuits, then it is going to act as a second order low pass filter. So what happens in this second order low pass filter? So why we are going for this second order low pass filter? We are going to observe now. We are going to observe now why we are going for this second order low pass filter, and what happens when we are considering this second order low pass filter. So this is the circuit for the second order low pass filter. Here you can see the output we are going to consider across the capacitor C, and input we are going to give in this side, the on left side, and the current flowing through this resistor is I1, and the current flowing through this capacitor is here. The current is going to divide into two parts at this node V1. That is, it is going to divide into I3 and I2, and then this I3 is going to flow through I4 and as well as to I naught. Hmm? So now we are going to write an equation for this such that nodal equation, that is nothing but the nodal equation. So if we are going to write the nodal equation, so we, that is nothing but I1, as we know that I1 is equal to I2 plus I3. I1 is equal to I2 plus I3. So this is I1. So this is nothing but I1, which is equal to I2. This is I2, and plus this is I3. So we are going to write this in the form of nodal equations. That is in voltages we are going to write KCL. So VI. So I1 can be obtained by, I1 is nothing but the current flowing through this resistor. I1 is nothing but the current flowing through this resistor. So when we are going to consider current flowing through this resistor, as we know that the voltage at this node is VI and the voltage at this node is V1. So VI minus V1 divided by R will gives the value of I1. So as this is the entering current, this current is going to divide into two parts. We can say that I1 is equal to I2 plus I3. That is how we have written here. So this is I1, and when we are considering I2, I2 is nothing but the current flowing through this capacitor. It can be given by, so as here the node is V1, and as here the node is 0, as here the node is 0. So V1 minus 0, SC into V1 minus 0. So as 0 is not having any value, so we are going to eliminate that. So SC into V1. SC into V1 minus 0 will become SC into V1. So we are going to write here only the SC into V1, SC into V1. And next, when we are going to write the equation for I3, so when we are going to write the equation for I3, so I3 is going to flow through this R resistor and the voltages at these two nodes are, and the voltage at this node will be V1, and the voltage at this node will be V2. So when we are considering this, the voltage at this node will be, sorry, V0. The voltage at this node will be V0. So V1 minus V0 divided by the resistance in this part. The V1 minus V0 divided by the resistance in this part. So this is how we have written this equation. Now we are going to solve this equation, and finally our aim is to obtain the transfer function. And the transfer function, we are going to observe the transfer function depends upon which factor, and what happens to the frequency response of this filter. What happens to the frequency response of this filter? So when we are going to use the two RC networks, what will be going to happen for the frequency response, and what are the changes we have obtained at frequency response, we are going to observe that. So now if we consider this, if we go on solving this equation, so vi by r, so we are taking this minus v1 by r to right hand side, and taking v1 as a common. So vi by r is equal to scr plus 2, because here we are having two v1s, which will become 2 into v1, so 2 divided by r, and minus v0 divided by r, this will be separate. So V1 minus V0 divided by R is equal to SC V0. Okay. So as we know that the current flowing through this resistor is equal to the current flowing through this capacitor. So we can write this equation as V1 minus V0 divided by R. This the current, that is I3, is equal to I4. So we are going to write SC V0. SC V0 CV naught minus 0, nothing but V naught minus 0, that is towards ground. So as 0 is not having any value, so we are going to eliminate that. So V1, from this equation we can write V1 is equal to SCR. So we are bringing this R to this side, so SCR plus 1, and V naught by R, or we are bringing this V naught by R also to this side. So then what happens when we are bringing this V naught by R to this side? Hmm? Then what happens? So now this equation becomes like this: V1 is equal to SCR plus 1 into V0. So this we are going to consider as equation 2. So now from 1 and 2 equations, so in the place of V1, nothing but in the place of V1, we are going to write, so in equation 1, in the place of V1, we are going to write this equation. So by replacing that term, we are going to get a VI by R, which is equal to SCR plus 2 divided by R SCR plus 1 into V naught. That means here we are going to bring the equation in terms of V naught and Vi. So we are going to remove this V1. We are going to remove this V1. So that is why finally we want the gain, that is V naught by Vi. For that reason we are going to do this. So finally V naught terms will be coming at the right hand side, and VA terms will be coming at left hand side. Then we are going to bring this R to the right hand side, as well as we are taking common V0 and bringing that keeping here V0, taking common from all this expression, we are going to take a common of V0, and then we are bringing this R to right hand side, or else we are bringing all this equation to the left hand side, and then we are bringing this VA to right hand side. Then the equation is going to become, by solving this equation, we are going to get a V naught by VA is equal to 1 by SCR square plus 3 SCR plus 1. So the transfer function will be, so 1 by CR whole square divided by S square. So by dividing the each term with a CR, nothing but a CR, we are going to get CR square, not CR square. So CR square. So this CR square will be cancelled, and here we are having 3 by 3s by CR plus 1 by CR square. And here next after dividing that, on numerator and denominator, we are going to divide it with the CR square. So here you can see. So the equation obtained will be like this. So this resembles like a characteristic equation, that is s square plus axs plus 1. S square plus as plus 1. As square plus bs plus 1. Nothing but this is looking like a characteristic equation. And hence we can write, as we know that 1 by CR, as we are assuming that 1 by CR is equal to omega naught, as we assuming that omega 1 by CR is equal to omega naught. So h of s will become omega naught square. So 1 by CR square means nothing but omega naught square. Okay, divided by s square plus s3 into omega naught plus omega naught square. So this is what we're going to get, the transfer function of this second order low pass filter. So when we observe here the transfer function, so here what are the changes we have observed here? So the gain remains at 0 dB, and the cutoff frequency FC. So here FC depends upon same, that FC is going to depend upon 1 by CR. Again, it is going to depend on 1 by 3R only. And this slope, you can see the slope here, the change we have observed, that is in the slope. Here you can see the change we have observed in the slope, that is slope becomes minus 40 dB per decade. Here in case of first order low pass filter, the gain will be minus 20 dB per decade. So here the gain will be minus 40 dB per decade. So for every decade, so for every decade the gain is going to be, for every decade you can see 0 to 20 dB, it is going to decrease 40 dB, and from 20 dB to 40 dB it is going to decrease again 40 dB, and 40 to 60 it is going to decrease again 40 dB. That means the slope in case of uh, in case of first order low pass filter, in case of the first order low pass filter, so the response resembles like this. So the response resembles like this. Okay, in case of for second order, the response becomes like this. So as we are going to increase the number of RC circuits, that is third order, fourth order, like that, and that means we are going to increase the number of RC circuits which are connected in series. Then this attenuation will be will come towards this line. So in such a way, we are bringing our practical filter response uh, nearer to the ideal filter response. That is an ideal filter response by considering the different by considering different number of RC circuits. That is the number of low pass RC circuits which are connected in series, which are connected in series. So we will stop here, and we will consider, we will continue in our next session. And next we'll continue in our next session. In the next session we are going to discuss about the high pass filter and its response. Thank you, students. Thank you for your support.